In this video, we'll be discussing elimination kinetics. In the last video, we talked about elimination, which is the process by which a drug is removed from the body. And we talked about clearance, which describes the efficiency of how this elimination occurs. We talked about hepatic clearance, which decreases the functional concentration of the drug by metabolizing it into more aqueously soluble metabolites, and we talked about renal clearance, which filters the drug or its metabolites into the urine to remove it from the body. Elimination kinetics focuses on how the elimination of a drug changes throughout the time that the drug is in the body. There's two major modes of elimination kinetics: first-order kinetics and zero-order kinetics. Which mode occurs depends on the concentration of the drug in the bloodstream relative to the concentration of enzymes and transporters involved in elimination of that drug. To simplify that statement a little, let's just focus on one class of enzymes that's involved in a lot of drug metabolism, the cytochrome P450 enzymes in the liver. These enzymes are going to follow all the properties of enzyme kinetics that we discussed earlier in the chapter on pharmacodynamics. So here's an example Michaelis-Menten curve for a cytochrome P450 enzyme. So on the x-axis, we have the concentration of the enzyme substrate, which in this case is going to be the drug that's being metabolized, and on the y-axis, we have the initial velocity of the enzymatic reaction. Remember that as the concentration of the substrate increases, the velocity is also going to increase until we've reached the point where all of the enzymes are saturated, at which point the velocity has reached the maximal velocity and will stay constant even as the substrate concentration increases. First-order elimination kinetics will occur when the enzymes involved in the metabolism and elimination of a drug are not saturated. So for the case of our CYP450 enzyme, that's going to be in this range of substrate concentrations here. In this situation, the rate at which the drug is eliminated is directly dependent on the plasma concentration of the drug. At the higher end of this first-order concentration range, the velocity of the enzymes is going to be near the Vmax, which means that more drug can be metabolized in a given period of time as the enzymes are working relatively quickly. But as the drug is metabolized, the concentration of it in the plasma is going to drop, which means we're going to move to the left on this x-axis and down the Michaelis-Menten curve. At this lower drug plasma concentration, the velocity of the enzymes is now going to be lower, so less drug will be metabolized in the same amount of time as before. If we look at this relationship on a drug plasma concentration versus time graph, we end up with this exponential curve. And let's just put some units on the x-axis, so let's say that this is 1 hour, this is 2 hours, this is 3 hours. We can see on this curve that in the first hour where the drug plasma concentration is at its highest, a lot of drug is eliminated. But now the drug plasma concentration is lower than it was initially, so we've moved down on this curve, and that means that our velocity of the reaction is going to decrease, and we're going to be able to eliminate a smaller amount of drug between hours 1 and 2. You can see now that this arrow, which represents the amount of drug eliminated over the first hour, is less than this arrow, which is the amount of drug eliminated over the second hour. And this pattern is going to continue as the drug plasma concentration decreases over time. The pattern that's happening here is a constant percentage of the drug is being eliminated over time. So in the first hour, 50% of the initial drug concentration is eliminated. And then in the second hour, 50% of the drug that was remaining at time equals 1 hour is eliminated. So the percentage of the plasma drug concentration that's being eliminated is always 50%, but the amount of the drug being eliminated is decreasing because the plasma concentration is decreasing over time. Okay, now let's consider what's going on the other half of this curve, which is when these CYP450 enzymes are saturated. This is going to lead to zero-order kinetics. In zero-order kinetics, the amount of drug that's being eliminated stays the same regardless of the plasma concentration. On the Michaelis-Menten curve, you can see that as we move from the high end of the substrate concentration range to the low end of the substrate concentration range, the velocity actually doesn't change very much. This means that no matter what the substrate concentration is, the enzymes are going to be processing the same amount of drug in a given interval of time. On the plasma concentration versus time curve, this ends up looking like a linear relationship because the same amount of drug is eliminated per unit of time. Zero-order kinetics is a really undesirable property for a drug because it is easy to take too high of a dose, leading to toxic effects. Under first-order kinetics, the higher dose you give, the more rapidly it will be eliminated from the body. Under zero-order kinetics, high doses are eliminated at the same rate as low doses, which means there's a greater risk of too much drug building up in circulation, causing toxic side effects. Just to see what that looks like on these two graphs, let's imagine that if you take a dose of a drug higher than this red line, you end up with toxic side effects. Under first-order elimination kinetics, if you accidentally take double that dose, you're only going to be exposed to that plasma drug concentration for 1 hour. Under zero-order kinetics, if you take double the dose, you're going to be exposed to that level of drug concentration for 2 hours. The vast majority of drugs are taken at doses that follow first-order kinetics. But it is important to be aware that there are a few common substances that do follow zero-order kinetics: ethanol, the anti-seizure drug phenytoin, and aspirin. And just as an aside before moving on to half-life, first and zero-order kinetics are named based on the rate equation, which is that rate is equal to the elimination constant K times the substrate concentration. In first-order kinetics, the rate depends directly on the substrate concentration, so the rate equation is going to be rate is equal to K times the substrate concentration raised to the power of 1. In zero-order kinetics, the rate is independent of the substrate concentration, so the rate equation is rate is equal to K times the substrate concentration raised to the power of 0, which simplifies down to just rate is equal to K. It's not super important to remember these rate equations, but it can be useful for remembering that first-order kinetics depend on substrate concentration and zero-order kinetics do not. The last thing I'd like to discuss in this video is the concept of half-life, which is the amount of time that it takes for half of the drug to be eliminated. This is a useful way to summarize the elimination rate of a drug. So in this graph up here for the first-order kinetics, we talked about how it takes 1 hour for 50% of the drug to be eliminated. This means that the half-life of this drug is 1 hour. This is always going to be the case no matter how much drug is present. So at time equals 0, we have 100% of our initial drug concentration. At time equals 1 hour, we have 50% of our initial drug concentration. At time equals 2 hours, we're going to have 50% of the drug concentration we had 1 hour ago. So that's going to be 25%. At 3 hours, we're going to be at 12.5%, and so on. The longer the half-life of the drug, the longer it takes for the drug to be eliminated. For this particular zero-order kinetics graph, we can see that it takes 2 hours to eliminate 50% of the drug. But for zero-order kinetics, the elimination rate is just dependent on time and not plasma drug concentration. So that means the half-life is going to depend on the initial plasma drug concentration. I think this can be a little bit of a confusing concept, so I'll draw out an example on the graph. Let's say that instead of starting at this concentration up here that we started with for the teal-green curve, we started at half that amount of concentration. But because this is zero-order kinetics and the elimination rate is independent of the drug plasma concentration, the rate that the drug is eliminated is going to be the same. So it is going to look something like this. And you can see that the elimination rate is the same because these lines are parallel to one another. If we look at this pink curve now, the half-life of this drug is going to just be 1 hour, even though this is the same exact drug as we were looking at before. So for zero-order kinetics, the elimination rate is independent of the drug plasma concentration, but the half-life is dependent on the drug plasma concentration. Going back to first-order kinetics, since that's how most drugs are eliminated, the half-life for first-order kinetically eliminated drugs can be calculated if you know the volume of distribution and the clearance. And the formula for this is the half-life is equal to the product of 0.7 and the volume of distribution divided by the clearance. Deriving this formula requires some calculus and is outside of the scope of the Step 1 exam, but calculations using this formula do come up, so it is worth memorizing. To summarize what we talked about in this video, the vast majority of drugs are eliminated through first-order kinetics, where a constant proportion of the drug is eliminated. This means the elimination rate is directly dependent on the plasma drug concentration. The half-life for drugs that follow first-order kinetics can be calculated using this formula. Zero-order kinetics, where a constant amount of drug is eliminated regardless of how high the plasma drug concentration is an undesirable property for drugs because it makes it hard to figure out the appropriate dosage. Common substances that follow zero-order kinetics are ethanol, phenytoin, and aspirin.